All right, so welcome back to the third part of this lecture. In the first two parts, we talked about how first we talked about how we can think of functions or signals as vectors, and we can think of systems as matrices. Then we talked about the Laplace transform as a unitary system itself, which maps one vector, the signal, to another representation, another basis for that same vector space, but in the frequency domain, where the bases of that domain were those test functions, e to the st. And talked about how we can also represent systems, those matrices, as, for causal linear time invariant systems anyway, as matrix valued functions in the complex plane. Right? So we talked about the space of transfer functions, which lies in H infinity, and we showed that the signal norm on those transfer functions, right, can be used directly, which is a representation, to infer properties of the system itself. And so the property of the system itself, the obvious one, is the induced L infinity norm, norm from L2 to L2. Right? So a system property in terms of a system representation. So properties of the representation versus properties of the system itself. So the problem we're faced with at this stage is that we don't really know how to parameterize or optimize, much less, this new space of system representations, this new class of system representations we refer to as transfer functions. And so we're going to then relate the properties of the transfer function now to properties of the state space representation, which we're more comfortable with, A, B, C, D. Right. But we're not going to do it directly in terms of this A, B, C, D itself. We're going to pose an optimization problem, or an LMI, on those system representations, which are equivalent to the properties of the transfer function, which are then equivalent to properties of the system itself. So a little roundabout way of doing things. Now, to get there, we need to restrict ourselves a little bit. We need to restrict ourselves to transfer functions which can be represented using state space systems, right? So the set of transfer functions is actually rather larger than the set of state space systems, right? Right. So, but we're only working in finite dimensions, and we only have these state space representations to work with. So we're going to have to restrict ourselves to the classes of systems which have transfer functions which can be represented using those four matrices A, B, C, D. Right. And so to do that, we have to we impose some restrictions on our set of transfer functions. So a subset of transfer functions. Right? And specifically, we consider the class of rational transfer functions. So this should be familiar to you if you've taken undergraduate controls, because you've probably very rarely seen any transfer function which is not rational. And by rational, we mean, we define it using this letter R here. It can be represented as the ratio of a polynomial in the complex plane, right, the complex variable, over another polynomial in that same complex variable. It's also there. So For example, right, if we had s squared plus s plus 1 over s cubed plus s plus 1, right? That's a rational transfer function because both of these are polynomials, right? So we were going to restrict ourselves to transfer functions which look like this, basically. A polynomial over a polynomial, and we give that a little letter, r, which maybe we should make it fancier, but that's what we have. So rational transfer functions. And then, of course, we would like those transfer functions to lie in our transfer function space, which is namely h infinity. Right. Now, you can have transfer functions in H2, so we're not going to dismiss those out of hand, and we'll return to them again later, because we do talk about H2 optimal control. So, but they're different spaces. Remember, H infinity and H2 are totally different spaces. And so we'll focus mostly on this case of transfer functions in H infinity. Right? But then, of course, as I said, we have to restrict ourselves to ones which have state space representations. And in order to do that, we have this intersection, right? So we define the space RH infinity, which is the transfer functions which are also rational. Right, so RH infinity is a set of rational transfer functions, where the transfer functions space, original one was H infinity, and we can extend that to RH2, right? So if our transfer function space was H2, we restrict ourselves to elements in H2, functions in H2, which are also rational, have numerator and denominator. Well, and why do we do that? Well, because specifically, any state space system, if you take the transfer function of that system, it's rational, right? And vice versa, any rational transfer function has a state space representation with a caveat, which we'll give on the next slide, that it be proper. Well, haven't defined proper quite yet. This is problematic, and we didn't introduce it before because RH2 and RH infinity, when you make that restriction, we lose a lot of the properties that we needed before for all the mathy stuff that we talked about. And specifically, these spaces of transfer functions, they're still algebras, they're still normed spaces. So they're still normed spaces because they have the same norm, H2 and H infinity. But they're not complete, right? They're not Banach spaces. And that becomes a little bit problematic where in sort of extreme cases, so for example, in the case of a delay system, right, where you have a delay in the system, right, that's not rational. There's no state space representation of a delayed system. And likewise, there's no rational H infinity representation of that complex exponential. Right. So we're getting rid of the delay type systems or any basically infinite dimensional systems. However, using this norm that we've defined, the H infinity norm, we can define a sequence of rational transfer functions, which actually converges in that norm to this exponential. And so, but of course, right, this is not in RH infinity, and so that's where we lose this property of completeness, right? There's a sequence of rational Pade approximations which converges in the right norm to this complex exponential, but is not, obviously this is not a rational function itself. Right? So we can have this weird situation where we have a limit of these transfer functions limit of systems in the H infinity norm, which converges to something which is not in RH infinity itself. And so we have all sorts of caveats, and we have to hedge all our bets at this point. But that's life. That's how it is. Yeah. So I said that any rational H infinity transfer function has a state space representation, and vice versa. Any state space representation has a rational H infinity transfer function. But we actually have to hedge our bets a little bit there, because that's actually, rationality is not good enough. You have to have a little bit more. The functions have to be proper. In here, you may use proper informally in all sorts of manners, right? In terms of, or in proper manners, in fact. But in fact, proper mathematically means something very specific when it's referring to elements of RH infinity, or RH2 for that matter. So for elements of RH2 or RH infinity, we refer to proper, meaning, well, because it's an R, right? It can be represented as a numerator over a denominator. We refer to proper to mean that the degree of Q is greater than or equal to the degree of P. So for example, if we had s to the fourth plus 1 over s plus 1, right, the degree of that numerator P is 4, and the degree of the denominator Q is 1. So because the degree of the numerator is greater than the degree of the denominator, this is not proper. And don't read too much into this, because this is not a great restriction to properness, but it's necessary. So for example, if we had s plus 1, right, if that was our transfer function, well, s plus 1 is not in H infinity. Why? Well, because, I mean, you just look at it, it's I omega plus 1, and what's the maximum value of I omega over the complex, over the frequency domain? That's infinity, right? Because omega goes to infinity, the norm of this goes to infinity, right? So properness is a reasonable restriction, right? Any function in H infinity will automatically be proper. What happens if the system is not proper? Well, it's not in H infinity, and therefore it must violate either causality, time invariance, or linearity. In particular, the property it violates is causality. So if you have say a transfer function which is a PD controller, for example, that looks like KDS plus KP, right? That's a PD controller. That's a transfer function for it. It's not actually a transfer function, right? By our definition, it's not a transfer function. Why is it not? Well, because it has its H infinity norm is infinity, right? So PD controllers are not in H infinity, therefore they must violate causality, time invariance, or linearity, and the thing that they violate is causality. Basically, because you should be able to use a PD controller technically to predict the future in some way. You see where the direction the system is going, that's the derivative part, and then it allows you to predict the future by following that derivative. So that's not allowed. So that's what we avoid when we say proper. And then strictly proper, we don't fuss too much about strictly proper here. Strictly proper is where the degree of the denominator is strictly less than that of the numerator. So say s squared plus 1 and s plus 1. The degree here is 1, the degree here is 2, and so that one's strictly proper. Whereas if you just had s squared plus 1 over s squared minus 1, right, this degree is 2, this degree is also 2, and so that's proper but not strictly proper. So, right, if we restrict ourselves to proper transfer functions, then we can say things like what we have here in this proposition 1, that a function is in RH infinity. Obviously, it has this, by definition, it has this rational representation, and then it's a necessary and sufficient condition for that function to be a transfer function in RH infinity is that it's proper, and it has no poles on the right half plane. Right? So obviously, if I have a pole in the right half plane, it represents an unstable system. So a stable input would produce a unstable output, which goes to infinity. Right? So that's the problem. Right? So restricting ourselves to rational transfer functions allows us to very easily tell if a transfer function is a valid transfer function or not. We don't allow unstable transfer functions into our block diagram. Those are not allowed. And we likewise don't allow PD controllers into our block diagram. Also not allowed. Now you can put a PD controller inside a block coupled with something else, but the overall block must be in H infinity. Right. So again, it's by our definition of how these block diagrams work, how input-output systems work, the systems have to be stable, that you're coupling together, and the systems have to be causal. Right. So that we encapsulate, we represent that, we talk about that as saying it has no poles in the right half plane and it's proper. All right. So now that we've restricted ourselves to rational transfer functions, we can create a one-to-one map between rational transfer functions in H infinity and space representations. Let's switch our color again. Go for pink, miss pink. So there's a one-to-one relationship between systems which have a state space representation and systems which have a RH infinity transfer function, right? One-to-one. So that's encapsulated by the theorem right here. It says that any stable state space linear system G is a state space linear system if and only if there exists a rational proper H infinity transfer function such that the system equals this multiplication operator with the inverse and Laplace transform. So there's a representation of that using the multiplication by the transfer function. Right? And likewise, the converse of that, right? If you're in RH infinity, there exists a state space representation which is stable, or so A is Hurwitz. So, right, there's a one-to-one relationship. That's what this theorem is telling us between RH infinity and state space systems. Right? And we can go a little bit further. We can actually give this relationship, well, at least in one direction anyway, between the ABCDs, right, and the transfer function itself. Right, it's something I think it's called the matrix pencil. I'm not actually sure about that right now, but there's this formula which you've probably seen before, which gives you the transfer function for that state space system. Now, I said they're one-to-one, but of course, the representation is not necessarily unique. So for example, similarity transformation of the internal states, X, right? We can use a different choice of X for our internal state, which is defined by this similarity transform. And so in fact, right, we could just plug this into the formula, right? We can, any state space system of this form for any invertible matrix T gives us the same transfer function, right? So they're one-to-one, but the map is not necessarily unique. So this map between transfer function and state space is a little bit dodgy. Right, so, but keeping that in mind, the result is still quite important. It allows us to go back and forth, or at least in theory to go back and forth between state space representations. So we can have confidence that if we have, for any A, B, C, D with A Hurwitz, then there exists a transfer function representation, and that has that representation, the properties of that representation give us properties of the system. Yeah. So now we've got, remember we have our map here, we have the system, we have the transfer function representation of the system, and we related the norm on that transfer function, that signal norm, to the induced norm on L2 of the system. And then now we're going to, by restricting ourselves to RH infinity, we're going to be able to say something about this transfer function norm using those ABCDs. Remember, they're not unique. We could choose a different ABCD with a similarity transformation, but that doesn't change anything. Through an optimization problem. So there's an optimization problem whose inputs are, or data is the ABCDs, and which tells us something specifically about that transfer function norm, which of course tells us something about the system norm itself. And that result, very important result, perhaps the most important result, which allows us to do optimal control, is the KYP lemma. And as I said, this is possibly, probably even, the most important theorem in this class. Or it's actually a lemma, but it's a theorem, but whatever. It's a result. Right? It bridges this gap between representation and in state space, and representation of in frequency domain, which tells us things about the system properties. Okay. So what is the result? Well, so say we have a state space system representation, and this is our standard notation for A, B, C, D. We don't always write it as like A, B, C, D because that's cumbersome and annoying. So we have this this special notation which allows us to go directly between A, B, C, D and the transfer function associated with A, B, C, D. C, S, I minus A inverse B plus D, right? The inverse, right, is going to give you that the ratio, the denominator, right? So the transfer function, right, and here I should actually put a little hat there. So this says, right, this relates directly, the norm on that transfer function is less than gamma, if and only if there exists a positive matrix X such that this LMI is satisfied. And this is, of course, an LMI because this is a matrix inequality. Right? So it's a very classical result which relates the property of the transfer function representation through an optimization problem to the system state space representation. So, in fact, actually, the KYP lemma predates LMIs. Right? People didn't think about LMIs when the KYP lemma, Kalman-Yakubovich-Popov lemma, was being created. It wasn't a thing. Right? And in fact, actually, the derivation of the KYP lemma was for the purpose of actually, people thought that testing these things was easier. And in a way it is, right? You just write out the Bodhi plot, right? The magnitude and the phase of G hat of I omega. And you look at the magnitude plot, and the maximum value of that is the H infinity norm. Right? So you can verify this optimization problem. So the original goal was then to take an optimization problem and turn it into a graphical test using the Bodhi plot by constructing the associated transfer function and finding its maximum norm, or its Bodhi plot. So people had optimization problems they wanted to solve, and they put it in this form, and then they constructed the matrix pencil, the transfer function, and drew the Bodhi plot and tried to verify feasibility of that, right? And this was before we had algorithms for solving LMIs. And so this was actually an algorithm for solving an LMI and not actually an algorithm for representing a system property using an LMI. So it was actually going the opposite direction. Of course, nowadays it's the importance is clear in the other direction because we can't really optimize Bode plots. Not optimizable. So we actually use this to convert the Bode plot optimization, the representation constraint on the transfer function, in terms of an optimization problem, which now is much easier to solve because we have interior point methods and so forth. We have YALMIP, right? But they didn't used to have YALMIP, so they did it the other way. Right. So important points, right? It's a linear matrix inequality. The variable here is x, right? This is a first constraint, strictly greater than 0. Second constraint is an inequality negative, but it's linear in the variable. It only appears linear here, here, here. This is not right now linear in C and D, but we will find a way to make it linear in C and D later. So, how does this work? What allows us to take this transfer function representation and convert it to an optimization problem on the system representation? And of course, if you've been paying attention in the previous lectures, you could already guess the answer. X represents a Lyapunov function. Right? Which is going to tell us something about the system properties. And actually, so technically, we don't actually go to the transfer function. We actually use this in this direction, in the sufficiency direction. So this implies this. 1, 2 implies 1. We actually use the system. We use that Lyapunov function to determine the system properties. The counter, the necessity, the sufficiency condition, so this implies this, we're not going to actually go over, right? And that actually does use the transfer function properties. But because it's complicated and not particularly illuminating, I'm going to skip it. It takes a while, so it requires a Hamiltonian, and I think it slows down things a lot. So we'll just prove sufficiency. And sufficiency, right, now that you're comfortable with Gramians and so forth, should be relatively straightforward, right? So basically, we're going to take the LMI, and we're going to show that that implies that the induced norm from L2 to L2 is less than or equal to gamma, which is, of course, as we've shown, equivalent to the H infinity norm of the transfer function less than gamma, right? So we're actually going to do this direction only. Right? And it's really, the converse, right, is more complicated, right? It shows that this implies this, but again, right, that's more difficult, so we're not going to do it. All right, so first of all, let's look at the LMI. This is the LMI, right, less than 0. Obviously, if this is less than 0, this term by itself is less than 0. So that's something actually we don't use very much, but we can state it anyway. It implies that A is Hurwitz by itself. So how does the proof work? Right. Well, it gets a little complicated because you got the epsilons here to make everything strict. The non-strict version of this we don't want to do because we don't have the sufficiency part. But so we try and keep everything strict. So there's a couple epsilons which keep appearing here, right? So we'll try and gloss over those to some extent. So because the inequality is strict, right, there exists some epsilons such that this is less than epsilon I, and we move the epsilon I into the inequality. We put it right there, so it shows up actually. We pull it out again, it shows it up right there. All right. So now we assume that the LMI is feasible. There exists some x. And now suppose that x, y, and u are a solution to the system, state space system. Right? So that they satisfy these equality constraints, right? X, of course, of 0 we assume to be 0, right? That's very important. Otherwise, the whole thing doesn't hold up, because 0 input would give you a actual output, and so the gain on the system would be infinity. So we need this constraint on the initial condition so that this induced norm is finite. Otherwise, that isn't true. Right? So suppose y and x are a solution to the system. Right? Now, what we do is we take a sort of augmented vector of x and u, and we multiply it on the left and the right by this big matrix here, which, of course, by assumption is less than or equal to 0. We define the Lyapunov function, as you would expect, by x transpose xx, although technically this is often referred to as a storage function, not necessarily a Lyapunov function. But we're gonna call it a Lyapunov function because it does actually prove stability in our case. Yeah. So, but we really remember this input-output properties. We're not concerned with internal stability, so technically it's a Lyapunov function on this internal state, but we don't really care about that internal state. All we do care about is the relationship between y and u. Right. So we'd say storage function just so that we don't get confused with what we're trying to prove, right? It's something that's going on internally. It's not native to the system, right? It's going on with a state which doesn't actually matter to us, right? Because there's that ambiguity in representation through the similarity transformations. Any case, so x and u are solve the state space system, right? X and u are assumed to be solutions. We multiply on the left and right by this matrix here. And here I've just dropped off the time dependence because it doesn't fit on the slide. But then, so we multiply through. So the x and the x comes through here and comes into here. So we sort of break up these parts a little bit. Then we look at this part. Well, it's, what is it? It's cx plus du. And we recall, since this is a solution to the state space system, that's just equal to y of t. So that's y of t here. And then we don't, on the first step, we don't do anything with the other part. The second step, this just goes over here, so we don't do anything with it. The second step, we've got the 4 blocks corresponding to this this matrix. So this is x, right? Goes there. We've got the cross terms here. These are the 2 cross terms, right? xbu, blah, blah, blah. And then we got the 2 block here. That's just the norm of y, or norm of u squared. This is norm of y squared. Right. Gammas are staying put, right? We've got gamma here, gamma here. Here's a gamma in the denominator from over here. So we look at this, and then, well, let's say we see some terms we can group together. So ax plus bu gets grouped together. Those 2 get grouped together over here. And on the other side, of course, right, we get this term and this term grouped together, and those come over here, right? And so it's just an algebraic manipulation. And then since ax plus bu satisfy the state space system, right, we can say that these 2 terms are x dot t. Right? And so we just, those go down here, right? And so now we've got this relationship here. And, of course, we look at this carefully, and what is that? Well, it's nothing more than the derivative of this Lyapunov function along solutions of the system. right? So derivative of the Lyapunov function going backwards that way. And these are just the inputs and outputs, the size of the inputs and outputs. So this is a storage function, the derivative of the storage function, or Lyapunov function. If we're comfortable with including states in the system. These two terms, of course, don't depend on the state being internal. We're going to have to get rid of that state term, though, because we're only interested in input-output properties. All right, so now we've got this inequality here. So it's basically that says that v dot plus the norm of y of t is less than or equal to, and here we have over gamma, is less than or equal to norm of u of t. So this says that the size of the output, and here I'll multiply through by gamma, the size of the output squared is less than or equal to gamma times the size of the input at every moment in time. So at every time t. But of course, we know that this is not true, right? The size of the output is not less than the size of the input at every point in time, right? It's just the integral of that function is less than, of the output is less than the integral of the input. And that's where the v comes in, right? It allows this to be instantaneously greater than the input, as long as the integral over time that satisfies the desired property. And so obviously the next step then is to integrate the whole thing with respect to time. So if we do that, right, we integrate the whole thing with respect to time, then, well, these two terms, right, become, of course, the L2 norm of the input. So gamma times the L2 norm of the input squared plus the L2 norm of the output squared. And then this term here, right, you integrate a derivative of something, right? Fundamental theorem of calculus. We take the values at the endpoints, the final value minus the initial value. Now t is going to infinity, however, of course. And so we look at this, and well, here we've shown that it's Hurwitz, so we can actually take this limit as going to 0. So actually, this term is going to go to 0 as t goes to infinity. And furthermore, because we assume 0 initial conditions, this term is also 0, right? Because v of 0 is 0, right? Because remember, it was x transpose x. Well, maybe I should have chosen p. But anyway, if this is 0, right, it's 0, right? So straightforward. So that definitely goes to 0. This approaches 0. In fact, actually, we don't need it to approach to 0 because then it just makes the inequality stricter. Right. So since v of 0 is 0, right, we can write these terms out, take the limit as t goes to infinity, and we get, well, take that as v of t. And this definitely goes to 0. And so actually, if we wanted to, we can move the left-hand side over here, negative v of t. And since v is positive, actually, this just makes the inequality stricter. So we actually don't need this property here itself. But we have it anyway just because we have it, right? So we assume the system is stable, internally stable. Whether you actually need that, again, remember, because we don't care about the internal state, we try and avoid statements like that, but there it is. So this, of course, becomes the L2 norm there. That becomes the L2 norm there. And now we're in a position we just multiply through by gamma, and this becomes the L2 norm of y is less than the L2 norm of u times gamma squared, and there's a squared term here. And so this term is strictly negative, and that's why we had all those epsilons there, to make this strictly negative in the end. And so we just take the square root of this whole thing, and we get that the induced norm of g, I should say, this is equal to the induced norm of G, which is the H infinity norm of the transfer function, so maybe being a bit messy there, is less than, so we proved that the induced norm of the system is less than gamma, and that implies, of course, that the H infinity norm of the transfer function is also less than gamma. So that allows us to relate then the properties of the system through an optimization problem to the properties of the transfer function and to the properties, or an optimization problem defined on these four matrices. Right. So when we come back, we'll take a couple extensions to that. So we'll talk about passivity, we'll talk about small gain, and we'll talk about the H2 norm. We're not going to dwell on any of these too much because, right, remember our real structure of the property of the system is in terms of H infinity, but there are a couple sort of generalizations which are useful to make in certain circumstances, and so we'll address them in the next and final part of the lecture.